Okay, hello, Sam here again. I actually just recorded a different video, but I changed shirts to create the illusion of this being a different day. But then I immediately told you, so illusion ruined. Alas, that's the way it goes. So this is the week 10 video, last video of the term, last week of the term, week 10. And we only have 4 questions. Some of the questions have multiple parts, but this should go pretty quick. Probably. And what we were talking about mostly is radioactive decay and this important term half-life. So let's dive right into that. Define half-life and illustrate with an example. So I want to note that half-life totally could be pertinent to consider in other types of situations that do not involve radioactive decay. But if but we're talking about radioactive decay in specific, so we'll have that be all of our examples. But anything that leads to something decaying or going away or being consumed in a reaction or something like that, um, this term half-life could apply to, as you'll see in a sec. So what am I drawing, by the way? I'm drawing a crazy big nucleus. That's like a bunch of protons. I don't know how many it is. Let's call it like, 100 protons or something. And then we've got all these electron probability shells. And actually, if I'm really going to draw a good looking atom, I need more space. Because we've got our nucleus with, again, a bunch of protons and neutrons in there. And actually, let's make some of these actually look like neutrons because neutrons, of course, are protons with an electron stuck to them. And then it's going to have, its 1s shell with a lone pair. Then it's going to have a 2s shell with a lone pair. And then it's going to have, sorry, not a lone pair, with a pair of electrons. Then it'll have its 2p shell. That'll be filled. And then it's going to have a 3s shell. And then it's going to have a 3p shell. And then it's going to start to have its D shells. Um, actually, sorry, we would have gone 4s. Point being, there's a lot of electron shells, and there's all sorts of stuff going on. This is a big atom. I don't know what it is. I said it had 100, so let's just call it element 100 for fun. That is, let's not go to 100 because I don't want to get involved with F shells. Let's say it had 104. There's 104 protons in there, in nucleus. And so let's call this Rutherfordium, RF, which I was not fully aware even existed until right now. I'm looking at the periodic table. So you have this atom of Rutherfordium, and every so often it's going to shoot off maybe an alpha particle. There you go. 2 protons just shot off. And now it's no longer Rutherfordium. Now it is 102 of those. And so now it became Nobelium. Now, I don't know if that exact reaction would happening, but that is the decay part. The decay part is that it started with 104 protons, and then it lost an alpha particle, and it had 102. So it decayed, it shrank, it changed into something else. So that's decay. Now, how does that pertain to half-life? Because let's say that we had a cup full of like 10 Rutherfordiums. What was RF like that? We've got like 2, 3, 4. Let's do 4. We have 4 in there. The half-life simply is how long it will take for half of those Rutherfordiums to have disappeared and become Nobeliums, which, become Nobeliums. So the question is, how long did it take for half of that? And that amount of time is the half-life. So the half-life is an amount of time. So it's going to be a day, a minute, a second, or really it's going to be 387 seconds, or it's going to be 294 years. For certain things, the half-life is literally dozens, hundreds, thousands, hundreds of thousands of years. Some things don't decay very much, which means their half-life is huge. Other things decay very quickly, so they have a quick half-life. So a half-life is an amount of time, and specifically, it's the time for 1/2 of initial sample to decay. Now, the crazy thing is this. It's not crazy, but kind of the cool thing. Crazy cool. If we had started out with a cup full of like 500 Rutherfordiums and waited for it to decay into 250, it would take the same amount of time as 4 decaying into 2. If we started out with 1,000,000 and waited for it to decay to 500,000, it would take the same amount of time as 4 to 2 or as 100 to 50. The more you have, the more likely that parts of it are going to decay. So that is a very interesting thing about half-life. So half-life is the amount of time for an initial sample to decay. So if you actually, let's do a really quick graph of this. I think is helpful. So it's not an excellent graph, but if this is the time, and let's say that the half-life, which is often written like that. So let's say that our half-life in this example is going to be like 1 minute. So here's our time in minutes. Oops, that says minutes. And here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 minutes, okay? And let's say our initial concentration of whatever the stuff is, starts out, let's call it 800. 800 molar. That's huge molar. Let's call it micromolar because it's more believable. So if our initial at time 0 is 800, after 1 minute, we're going to be down to 400 already. And after 2 minutes, half of that. And after 3 minutes, half of that. 100. And after 4 minutes, half of that. Now you can see that each minute that goes out, we go to half, but we're never going to get to 0, at least on a molecular level. It's kind of a Zeno's frog kind of thing. Every half-life, you lose half of it. That was a terrible drawing. Let me see if I can do that better. I kind of doubt I can because it's kind of hard doing this, but all right, it's kind of all right. That was good enough. So I want to point out the half-life is not linear, or I should say, the concentration versus time function is not linear here. The half-life, when we plot this by half-life, you get this exponential decay that comes into play. So that's what a half-life is. It's the amount of time for half of your initial sample to decay. So initial means whenever you start measuring, by the way. So if you started measuring here, you would call that initial. And the thing is, it doesn't matter where you start. After 1 minute in each one of these, you're half from where you were. That's the concept of half-life. And one thing that's helpful about it is this situation right here. So the half-life, if you think about it, actually, I'm not going to try to derive this because did not prepare to do that, and I would take too long. I just want to point this out. The natural log of 2, which has to do with that exponential thing, over the rate of decay. So a half-life is an amount of time. It's time. A rate is going to be the change in concentration over time. So the half-life as time is going to be the log of 2 over the change in concentration over time. And so the time ends up flipping up top, and this divides, and that's how we get a time statement. And we're going to use that to solve these questions right here. So plutonium, again, it's a huge atom with like 1, 2, 3, 4. I'm kidding, I'm not going to really draw it. 239, but pretend I just drew 239 protons. That would have been funny if I counted that high. And then it's got a just ton of electrons, and it's eventually going to decay. And it's going to shoot off like an alpha particle or maybe a beta particle or something. And it's going to become slightly smaller. It's going to become something else. And it looks like it takes, see, this is a good example. The half-life for half of your sample of plutonium, it's going to take 24,000 years. So if you started out with 1 gram of plutonium, after 24,000 years, you would have half a gram of plutonium left. And after another 24,000 years, you would have a quarter of a gram of plutonium left. So let's see here. So again, it doesn't matter how much you start out with. However much you start out with, you're going to have half of that after the half-life. But what we need to find, they tell us the half-life. So the half-life is 24,000 years. That's the half-life. It's a time. 24,000 years is the half-life, and that's going to equal the natural log of 2 divided by the decay rate. So to solve for the decay rate, lambda is, we're just going to cross multiply those, right? Multiply each side by that lambda, divide each side by 24,000, get that. Unit-wise. Okay, so natural log of 2 is like 0.65, right? 0.695? 0.693. So we can say that lambda is going to equal 0.693. That's the natural log of 2. You know, you could keep that as natural log of 2 in your calculator if you want to be extra exact about this. And when we divide the natural log of 2 by the given half-life of 24,000 years, we get 2.888 times 10 to the negative. Let's see here. 1, 2, 3, 4, 5. Per year. So out of 100% that you start with, you lose that much per year. And if you think about it, it makes sense. That's why, right, that's 0.12. That's what chunk of itself out of 1 you lose per year. So it makes sense that it takes 24,000 years to lose a half. So that is the decay rate. So they say you start out with, let's say, once again, let's say we start out with a gram, 1 gram, and you take 1,000 years. They're giving us 1,000 years, and we know that this loses that much per year. So 1 gram times 1,000 times that is going to be 1 times 2. I mean, the 1 part, obviously, we can just get rid of, but minus 2. That's what 1,000 times that is. So 0.02888 grams lost. That's how much it will lose over 1,000 years. And we started with 1. So 1 minus that is going to be 0.7722. I think I am going to do the responsible thing and make sure. I feel like I just slightly messed something up there. I super messed something up there. Oh yeah, duh. Good thing I busted out a calculator. So after 1,000 years, you're going to still, from your initial gram, you would still have that many grams left, which makes sense because it takes 24,000 years to lose half. So after 1,000 years, you would have basically 99.97% of your sample left, or your fraction, you would have that out of 1 gram. You'd have 0.997 out of 1 grams left. So once again, they gave us a half-life, they gave us a time, we found the rate, lambda equals the rate. We found the rate from the half-life they gave us, because half-life, the rate is just the log of 2 divided by half-life. We found the rate, and then we just applied that rate to the time period that was given. That yielded that we would lose basically that small fraction in 1,000 years. And did I do anything wrong there? I hope not. I don't think so, but maybe. But that's approximately correct. I think that was correct. Okay, so first off, we have T208. I believe that's an L. I wish L's and I's don't look the same. It's got to be an L. It can't be a capital I because this right here, right? That can't be a capital I because no element on the periodic table is abbreviated with 2 capital letters. So that's definitely TL, which is thallium. There it is. It's thallium. I just found it. So that's thallium. I'm going to make my L look like an L. Thallium, by the way, is element 81. It's got 81 protons. And they're saying it's going to lose a beta particle, beta decay. Sorry. I've got beta decay some grass pollen or something. My cat looked at me. Usually my cat sneezes during these videos. By the way, Diego, this is the last video of the year, so you have to say hi. This is my cat. He was busy napping, and now he's like, "What's going on?" He's like, "What's going on?" Okay, cool. Hey, it wouldn't have been an internet video without a cat in it, right? So, beta decay is essentially when you lose an electron. And when you lose an electron, then one of these neutrons, which is secretly a proton with an electron on it, and then you lose that electron, so your proton becomes, so your neutron becomes a proton. That drawing was terrible. Let me draw that better. Here's a neutron, and a neutron is secretly a proton with an electron on it. So, if it loses that electron, which is the beta particle, it becomes a proton. What that means is our proton number right here is going to go up. So we're going to lose a beta particle, which looks like that, which is, again, it's just an electron, which really means in our mass and charge situation, this is going to go up, right? We're losing it, and it's negative. So that's going to be minus -1. So it's going to become element 82, which is lead. So the isotope produced by the decay, when it loses an electron, the isotope produced, the mass didn't change because that neutron became a proton, but the mass didn't change, but the number of protons did. And it's lead 208. The 82 defines it as lead. 208 is the total mass. So the half-life is 3.1 minutes. How long will it take for 99% of that sample to decay? So this will be many more. This will be a lot of half-lives probably. So let's figure out the decay rate. If the half-life is 3.1 minutes, then the decay rate is going to be the log of 2 divided by 3.1 minutes. Which is so it looks like the decay rate is 0.22359 per minute. So we're going to lose that much of our concentration, that fraction of our initial concentration every minute. So if our initial concentration, initial, you do that little 0 right there for not. Our initial concentration is, let's call it 100. And the final concentration is, so it's going to decay, 99% is going to decay. So the final concentration is simply going to be 1. So how long does it take to get from 100 to 1 at this rate? So the thing is, I think I need to use a logarithmic or exponent to solve this. Let me think about this for a sec here. So, I mean, one sloppy approach is just to run half-lives a bunch of times. I don't like that approach, but let's do that really quick and then come up with a more elegant approach. So by the way, here is Desmos. This is what I've been doing a bunch of calculations in. So let's see how many half-lives it takes to get from 100 to 1. 100 divided by 2. That was 1 half-life. Divided by 2. So 1 half-life. Two half-lives, we get to 23. 3 half-lives, we're at, oh wait, oops, there we go. 3 half-lives, 4 half-lives, 5 half-lives, 6 half-lives. After somewhere between 6 and 7 half-lives, we got less than 1 left. So we can say based on that, it's somewhere between 6 and 7 half-lives. So now let's do some algebra and see if we should get that. So for B, we just figured out that to get from 100 to 1 via dividing by 2 over and over and over equals between 6 and 7 half-lives. So 6 half-lives, if the half-life is 3.1, that would be 18 minutes. I'm ignoring the 0.1 for a sec. And 21. So it's somewhere between 18 and 21 minutes that we are going to decay 99% of our sample. So this is pretty fast, right? That would happen. After, somewhere in between 18 and 21 minutes, we're going to have shot beta particles off of 99% of the sample. So let me think. So if we're going to say that the, let me see, what? There's a formula that's basically this that I'm not applying correctly here to get this exact answer. Let me think about this for one more sec. I mean, like, the way I just solved it is not excellent, but kind of works. Okay, so if we have this rate, here's I think what we'll do. So we're gonna say it's x minutes. Let me change the color here. And I don't know if this grid is helpful. I did that one little plot earlier. That's why I have this on a grid setting. I don't know how it looks on YouTube. So we're gonna say x minutes times x minutes. I'm not gonna use x. Let's call it q. We're gonna say q minutes, and our rate is 0.22359 per minute, and we want it to equal 0.01 of what was left. So if I'm thinking of this correctly, I feel like I'm super not doing this correctly though, because I'm solving this as if it were linear, which it is not. So let me see here. I kind of want to pause the video and go look for this, but I don't know if I can easily connect it back to the video. So let me just see if this gets what I want, but I don't think it will. Yeah, I just got 22 minutes if it were linear. I mean, maybe that's right. Because if we do 3.1, let's see here, 3.1 times 7. Yeah, so that's not quite like that. We have to do a ratio. Here's what it is. This is what it is. We have to do a ratio of our initial. This is right. Oh, come on. Why are you disappearing on me like that? Whoa, sorry. We just had a weird laggy thing. This is what it is. For our half-life, so our time for this, we want our concentration of initial compared to where we're at now for our final. This is right. It's that ratio divided by the rate. So if this was 1, the final is going to be 0.01. And I'm basing this on the half-life thing, because if this were half-life, that'd be 2 and 1. Our initial would be 2, and that'd be 1. So there we go. So 1 divided by 0.01, I'm pretty sure is simply 100. Let's confirm that. 1 divided by 0.01 is 100. There we go. So T is going to equal 100 divided by... Oh, what about the natural log part? It's also the natural log of this. There we go. So the natural log of 100 divided by point by our rate. So I feel like this is actually going to be correct now. So the natural log of 100 is 4 point blah 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 divided by 0.22359. There we go. And now I just got 20.5, which this is exactly in that range that I knew would be in. 596 minutes. So there we go. That's the answer. Sorry, it took me a sec to remember how to set that up. I had to figure it out based on the half-life thing, right? So I knew it was half-life, so the top thing represents half somehow. How would it do that? Because 2 is the ratio of initial to final when you're talking half-life. So it's the log of that ratio, natural log of that ratio. So the natural log of initial to final, when we're talking about a 99% change, is 1 to 0.01, which is 100 is the ratio. And so there you go. I'm pretty sure that that is correct, and it definitely makes sense. So what percent, so that's B. So let's figure out part C. So again, part A, we're talking about this thallium decaying into lead. And it looks like if we want to decay 99% of it, it's going to take 20.56 minutes. And then it says after 1 hour. Okay, so first off, notice that we're at a different unit of time. So it's actually 60 minutes, right? Because our rate that we had been given up here for the half-life is in minutes. So we need to talk in minutes. So the decay rate, we've already solved several times here. What was our 0.22359? So that's like 22% basically per minute. And we're going to start at 1. We're going to run this for 60 minutes. But again, it's not linear. We have to set this up to be a logarithmic situation. Or maybe an e to the... No, I think we're going to do log. So we've got 60 minutes is the time. And 60 minutes is the time that the natural log of some ratio divided by the given half-life. I'm sorry, by which I meant to say divided by the calculated, rather, rate of decay. There we go. Okay, so this actually shouldn't be too bad, so we're going to multiply 60 by that deal. Let me grab that over here in Midesmos. Here we go. So 60 times that. So I'm going to multiply both sides by that denominator. That gives us 13.4157 equals the natural log of x. Now we're just going to e to the both sides. So e to the 13.4157 is going to equal x. So let's bust that out. E to the this. Here we go. Whoa. Something awry. Is that right? Maybe that's right. 13.41. Yeah, I guess that's correct. But let me think about this. Because this does not make sense to me at this moment. Oh, maybe it does. So, based on what I just solved, x equals like a huge number. 6.66 times 10 to the 2, 3, 4, 5 times 10 to the 5th. So that's the ratio of initial to final. And it says what percent remains undecayed. So the final is very small. So let's invert that. So 1 divided by that. One over this. No, it's positive 5 equals, which this makes sense. 1, 2, 3, 4, 5. That tiny little fraction, so like a tiny little fraction of initial is what's left. And that makes sense because the half-life was 3 minutes basically, right? The half-life is 3 minutes. We just ran it for 60 minutes. That's 20 half-lives. After 20 half-lives, the ratio of what your initial was to final is like almost a million. It's like 600,000. And so the fraction of what's left is 1.5 times 10 to the minus 6th. It's like a millionth of what was left. And again, that makes sense because, like, look up here. After 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 half-lives, we're basically at 0. So keep stretching that out. We're never going to get to 0 according to this theory. Now, that said, if you actually had an actual physical sample, there's hypothetically a specific discrete quantity of particles that could decay, so eventually you would get down to 0. But looking at this as a more of an amorphous quantity of stuff as opposed to discrete individuals, which is how we typically talk about chemical substances in terms of like mass and moles, not in terms of individual parts. It's basically you're gonna have to keep going for many, many half-lives before it's all gone. So after 1 hour, pretty much virtually all of our thallium-208 is gone, and virtually all of it has become lead-208, which I believe is a stable isotope and will not degrade. And the tiny amount that's left is, you know, take off 2 for the 100, so 0.00015%. So teeny, 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 teeny fraction of a percent. All right, let's finish off this last one, the last couple questions of the year. Awesome. So isotopes, such as aluminum-26, look, huge half-life, 72,000 years. are believed to have been present in our solar system as it formed, but have since decayed and are now called extinct nuclides. So that's funny because at first I thought that this was like a big number, but then they're like, nope, the formation of the solar system was so long ago that that's nothing. 72,000 years in the context of the life of the solar system is nothing. So it's an extinct nuclide. There's none of it left. It's had enough time to basically go away to nothing, like we were just talking about. Okay, so it can either give off a positron, which is the opposite of that beta that we just talked about, or capture an electron. So let's write both those out. So 26 Al and aluminum, according to my periodic table, element 13. So that's normal aluminum. And, oh, sorry, it's not. I think normal aluminum has another neutron or two. So if it were to decay by beta emission, that means it's giving off a beta particle. There we go. Beta is almost B, but not quite. And that means that we're going to go, beta is a plus on that, but we gave it off, so we're going to lose one. We're going to lose one from our lower number, so it's going to become 12. And we did not lose anything from our top number. Element 12 is good old magnesium. So it became, in that method, it became magnesium. Now with electron capture, it's the same thing actually, except for, well, it's the same result, I should say. The difference is instead of losing a positron, we're going to gain an electron. So the electron is on the left side of the arrow, right? Left, right? The electron's on the left side of the arrow for electron capture. And that means that electron is going to go find a proton in the nucleus and convert it to a neutron. So the mass is going to stay the same, but the number of protons will have gone down. And we get the same result. So the big difference is positron emission, we lost a positron. And in this time, this side, we have electron capture, and we've gained an electron. So those are those two transformations. So we have one left. The Earth was formed 4.7 billion years ago. How old was the Earth when 99.12345 6 of those had decayed? So we're given a half-life. This is just like that last problem we did, just with a few more digits. So we saw in our last problem that 20 or so half-lives would be expected. So right off the bat, I'm going to expect this to be approximately 20 half-lives. So let's see. How old was the Earth when this happened? So we started out with some amount. We have some initial amount of aluminum 26. And eventually, that's going to decay into what we're calling the final amount. And that ratio, according to the terms of this problem, also, I just realized this pen is like very thin. Give it a little more heft. So that ratio, if that much of it is gone, that's the amount that's left. Oh man, it's so small. So how do I write this rationally here? So 1 minus 0.99, and then it's 1, 2, 3, 4, 5, 6. I'm saying 1 instead of 100 here because of the percent, and that's why I did 99 point blah 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 as this. So that's, I'm only doing this. This should be really easy. I'm doing this so we can make sure we have the number of decimal places correct. We're going to borrow this all the way over, 0.1, and it's zeros. So that's 7 zeros. I'm going to move the decimal place 1, 2, 3, 4, 5, 6, 7, 8. 1 times 10 to the minus 8. That's how much is left. So if we started with 1, that's how much is left. So it's 1 divided by 1 times 10 to the minus 8th. That's the ratio of initial to final that they're asking about. So the length of time is going to be the natural log of that ratio over the half-life, which is given to us as 7.2 times 10 to the 5th years. So that's the rate, right? That's the decay rate. So we're solving for t. I was about to do some algebra, but we actually don't really need to do algebra. We just have to do some calculations. Where did my Desmos go? Here we go. I'll bring Desmos back on screen for you for these calculations. So 1 over 1 times 10 to the minus 8th. So that's our ratio. And I guess I could have done that in my head. That is 100 million. Yeah, 100 million. Okay. So the natural log of 100 million. 18.42. So that gives us that the time that has passed for that much of it to decay equals 18.42 divided by 7.2 times 10 to the minus 5. And actually, just as this equals the natural log, and that was of 100. Oops, is that 100 billion? No, that's 100 million. That's 100 million. That's what that was. Over. Okay. Oops. So that should not be negative. 72,000 years. But I think you can see right away, hopefully, maybe, that this is going to be a fairly quick time, which makes sense based on the premise of this question. This is an extinct nuclide. It's an extinct nuclide, but we'd expect it to go real fast. So we got 2.55 times 10 to the minus 4 years. So how old was the Earth when virtually all of the original aluminum was gone? This is like a misnomer. We don't really need to know that because the Earth was like less than a year old. So let's see. That amount. So basically instantly is what they're saying. Wait, that doesn't make sense though. Hang on. Something's real off here. Let me think about this. What did I do wrong? I must have done something wrong here. That's the initial to the final. That's the ratio of how much it changed. It took 2.7, 7.2 times 10 to the minus 5th. I definitely did something off here because we're expecting this to be like 20 half-lives, which should be like 7 million years or something. What did I do wrong? Let me think about this. I must have set up some detail of that incorrectly. And then the other thing I did wrong. Well, first off, I have like 900 browser windows open right now. There we go, looking for my Desmos. Okay, so that ratio of how much we started with to how much we're left with, that makes sense. That ratio divided by that half-life, I think that makes sense. Maybe I have an extra 0. That's probably what it is. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. No, I don't have an extra 0, so that's not it. improve it by going like this. Yeah, that's all the same. That's all the same. What the heck? Why? Because again, just like to go from... Let me see if there's like not that many things I could have done differently. So what if I put this on top? It still doesn't make sense, but that's what I'm going to try. So let's actually invert it like this. I'm going to go... This is a weird way to do this, but what I'm doing... Okay, well, luckily that makes less sense. So, what did I do wrong? Duh! I got it. It's because okay. I said it. So, this was supposed to be the half-life. So that should have been there. That's what the problem is. We have 2 point... So first off, we have to figure out the rate, and then we're going to plug it in. I apologize for running you through that, but it's good because now I realize what I was doing wrong. And it's exactly the kind of thing that you might do wrong on your final. So let's be clear that the way I set that up is for the half-life. In particular, I don't know my lambda yet. So 7.2 times 10 to the 5th is going to equal the natural log of 2 over my lambda. There we go. So lambda is the log of 2 divided by that. And now we can solve it, and it makes sense. And I think the most important thing educationally here is that I messed up, but I noticed I messed up because the answer just did not make sense. The half-life was 72,000 years. I just got an answer that it would be like a day or less. That does not make sense. So I definitely encourage you to always be asking yourself, does the answer that I just got make sense? So to that end, let's redo this a little bit. So the natural log of 2 divided by the given half-life will give us our rate. There we go. So our rate is 9.6 times 10 to the minus 7th per year. Tiny fraction. There we go. So now we can solve this. So now our actual time, that's what needed to be on the bottom. So our actual time is going to be the natural log of that ratio. That was correct. The natural log of 100 million, which is at 18.42, but now it's divided by 9.6 times 10 to the minus 7, which makes so much more sense per year. That's per year. We're dividing by per year. That's why the answer is going to be in years. So 18.42 divided by 9.6 times 10 to the minus 7. That was so wrong. That divided by, I could do this other ways, but I like to do it like this sometimes. There we go. That's the number that makes sense. 19 million years. 19,134,000. So 1934 approximately. There's some other digits, but that gets us there. Years. So this makes sense. It took 19 million years for all of the aluminum-26 to decay, but compared to the 4.7 billion years, that was very quick. In fact, let's just bonus really quick. See what fraction of the Earth's age that is, and then we're gonna, for reals, call it a day. So we're gonna take this number and divide that by, what are we calling it? 4.7 billion. So 4.7, 1, 2, 3, 1, 2, 3. Is that right? There's 1,000, a million. Oh, we need one more. 4.7 billion. So look at that. Let's do that whole thing times 100. That's the percentage of the Earth's life. So 0.4%. That's how long that aluminum lasted. So after about 0.4% of the Earth's life to date, because the Earth's life keeps getting longer and longer, but from approximately now, it took 0.4% of its life for all of that aluminum 26 to decay. Okay, so that is the answer. Once again, we all mess up. Try to catch yourself when you do. You're going to. I mean, probably. Most people do. I do. I do a lot, but I catch it a lot too, so that's the important thing. Cool. Thanks for watching. I hope that was helpful. Attempt to let us know if it was not, and always pay attention to your units. The units are the answer in chemistry. And like, study hard, be nice, and have a good one.